Started again. Okay, like I said, you are masters of A-star search. However, whether or not A-star search turns out to be the amazing tortoise hare that you hoped depends on how good your heuristic is. A heuristic which is more accurate, right? It's got to be a lower bound, but the closer a lower bound it is, the less work you will do exploring nodes which turn out to not be optimal. All right, so most of the work in practice in solving a hard search problem is not coding A-star. You'll do that once, it'll work. It's coming up with an admissible heuristic which is appropriate for that problem and effective. Okay? Often, admissible heuristics come from a single recipe. You can come up with an admissible heuristic however you like, as long as you can show that whatever number you've just computed is going to be a lower bound. Okay? But there's a common recipe that people use a lot, and that is to use relaxed problems. So for example, let's say we've got the Romania problem, and the heuristic is the straight line distance from wherever you are to your goal. You can think of that as a relaxed problem in the sense of, rather than having to stick to the roads, what if you also had direct roads between any city? They would have this cost. The shortest paths would always use those roads. And in that easier pathing problem where you get these bonus roads where you can drive straight there, this is the shortest path. So you can often come up with a heuristic or prove that it is optimal, or prove that it is admissible by this kind of reasoning about a relaxed problem. Here's another case of a relaxed problem. Here's Pac-Man. There's some shortest path that kind of dodges the walls in the right way. But what if we relaxed the problem? What if we made it easier, right? So what if we had Pac-Man could not only move into a free space, Pac-Man could also move into a wall? Well, then the Manhattan distance would always be the shortest path. And so we know it's going to be a lower bound to the true cost, because those new operators we added couldn't have made anything harder. It couldn't have made any of the paths longer. Right. So that kind of reasoning will help you in your project ones as you're asked to come up with admissible and, in a second, consistent heuristics for various problems. Okay. It turns out in practice that inadmissible heuristics, that's ones that slightly overestimate, they can be very useful. They can often accelerate the search, but there is a cost, and the cost is, one cost is optimality, and there's another way to set it up where the cost is efficiency. But what you should have in your head is inadmissibility is something that might get you a solution faster, but it puts you into greedy search territory, right? It puts you into territory where you might get the wrong solution fast. So let's see some examples. Well, here's the 8 puzzle. How many of you have played with an 8 puzzle? Really? Wow. How many of you enjoyed it? Yeah, so it turns out they've been superseded by other games for a good reason. They're not super fun, but we can think about them as a search problem. The search problem is you have some start state where the puzzle's scrambled. You've got a goal state shown to the right where usually there's a picture on these and you want the picture to look right. But let's just imagine mathematically there's that we want all of these numbered squares to be in their target position. So what are the states? Well, kind of conceptually it's really simple, right? The states are, let me get my pen back. The states are things like this. They're configurations of the board. Remember last time we had this big distinction of world state, which was very rich, and then search state, which was kind of only the important parts of the problem. When you've got a puzzle, essentially the world is the problem, right? In a real 8 puzzle, there's like dust on the board and there's your kind of cat clawing at your foot while you're solving it. That's the stuff in the world state you don't consider. But when we're just talking mathematically about the puzzle, we are already in the abstracted domain where there's kind of there's kind of no cat clawing at your feet or whatever. All right, so what are the states? They're things like this. In code, they might be a tuple of numbers. They might be a 2-dimensional array that says what is in each position. And of course, you have to say where the blank is. All right, what are the actions? Well, from any square, like from here, the actions are I can move anything adjacent to the blank into the blank. So from the start state, the branching factor at the start state is 4. There's 4 legal actions at the start state. What should the cost be? Well, probably 1, right? If you want to solve this thing as quickly as possible. But like, you know, maybe the number 3 sticks and that's more expensive to move. You could have some non-uniform cost. But kind of in the obvious formulation of this problem, the costs are just 1. This isn't a naturally weighted problem. All right, so now you know the 8 puzzle. We can take a start state, we can stick it into uniform cost search and get an optimal solution to the goal. Notice that if you stuck it into another complete but not optimal search, you would still get a solution, right? If you have a complete algorithm, it just wouldn't be the shortest solution. You may or may not care. So if we want to use A star, we need some heuristics. So here's a heuristic. Remember, a heuristic is a function from a state to a number. So one heuristic is the number of tiles misplaced. So in the start state, what's the value of this heuristic? Well, it depends whether you count the blank. It's actually important you don't count the blank. So here it is 8. And what's the heuristic here at the goal state? 0. That's usually a good sign, right? If the goal states don't work out to be 0, there's something wrong with your heuristic. All right, so why is this admissible? Can we argue this? Well, we can argue it mathematically. How might we argue mathematically that we can't solve this any quicker than 8? Any short argument? Yeah. Right, every misplaced tile must eventually be moved at least once. And in any given, importantly, in any given action, you can only move one tile. And of course, the blank moves too, and that's why you have to not count it as a misplaced tile if you want to use that argument. Okay, so it's admissible because in the relaxed problem, so one argument is just everything has to move once. That's a mathematical first principles argument. There's another argument from a relaxed problem. What relaxation of this puzzle, a strictly easier version of this puzzle, has that as the actual solution? Yep. Right, this is the version where you break all of the tiles off, and in any action you can move any tile from where it is to exactly its target. That is strictly easier, and in that one we know that the shortest path will always be the number of misplaced tiles. All right, so you might think that saying the start is 8, maybe it's actually quite far, maybe it's 20 away. Even so, these heuristics, even if they're not perfect, can save you a lot. So here, let's look at some numbers. So these columns are, obviously, if you start with a goal state, the search is going to be quick. If you start with something very far from the goal state, the search is going to be slow. This is the number of nodes expanded. This is actually in a graph search. We'll see in a second. This is the number of nodes expanded with uniform cost search, which, is there a heuristic for which uniform cost search is actually A star? Let's think about it. Yeah, I heard it. I heard 0. If you feed A star search the heuristic 0, it's just going to go along adding 0 to everything. The F's are going to be equal to the G's, and it's just going to be uniform cost. All right, so here's uniform cost search, which is essentially the heuristic 0. And you can see that as the solutions get farther away, we have to do more and more work to find them. And in fact, it kind of explosively more work. If we use this number of misplaced tiles, it reduces the work a lot. It's a big difference. Okay? But we can do better. How can we do better? If you either thought of it or read it in the 40 milliseconds it was up. Okay, it is true that each tile that's misplaced has to move at least once before it gets home. Can you say something stronger about how much it has to move? Yeah, so it has to move at least its Manhattan distance. So wherever that tile is, ignoring whatever is going on in other tiles, it has to move at least its Manhattan distance in order to get home. And remember that every time you make a move, you can at best reduce the total Manhattan displacement by 1. And so if you had an easier 8 puzzle, here's the relaxation, where any tile can slide in any direction at any time. In particular, this is the real 8 puzzle, where we relax the constraint that the tiles can't occupy the same space, right? So it's the same actions, they kind of do the same thing, but now it's legal to move a tile onto another one. It's actually even a little bit more relaxed than that because we can ignore the blank. That's the total Manhattan distance, and what's that for the start state? Well, number 1 is 1, 2, 3 away, and we could add that up for all of them. So that's going to turn out to be 18. That's a much bigger number. So we don't even know what the H star is, but we do know mathematically that it's 18 or larger. And this is a larger number than 8. Presumably, it'll be more efficient. Does everybody see why this is admissible? Okay, let's see what happens. Well, when you're close to a goal, it doesn't actually help. But as you get farther, it helps more and more. Okay? All right, so the tighter your heuristic is, the closer it is to the actual true H star, the faster your search will be. Okay, are you ready for an even better heuristic? Okay, what if you use the actual cost to solve the problem from that state as the heuristic? Is that admissible? Yes, it's admissible. Would you save on the number of nodes expanded? Well, actually, let's do a thought experiment. What the heck does A star do? It starts with a start state, and what would the F cost of the start state be? It would be 0 plus the solution cost, so 22 or whatever it is for that puzzle. Okay, what happens when you look at the children? Well, the optimal ones have what F cost? That same F cost. The non-optimal ones have bigger F costs, and you'll never get to them. So it turns out that if you use H star as the kind of actual cost as your heuristic, it's admissible, right? It's as good as you can get, and the only nodes you'll expand are ones along optimal paths. Okay, so what's wrong with this wonderful plan? Right, so like computing H star is actually the same as solving the search problem. And so now if you have a magic oracle that tells you H star but doesn't tell you paths, this is a slightly weird way of turning that into paths. That probably won't ever happen. But you know what's wrong with it is, in general, with A star, you're going to have this trade-off. You can spend forever doing search problem to solve the problem and compute H star, and then the A star search itself will expand very few nodes. But each one of those nodes will be as expensive as the original problem. Or you could give it 0, right? And if you give it 0, you spend no time computing the number 0, but of course you're doing what kind of search? Doing uniform cost. So you want to find some happy middle ground where the heuristic isn't too expensive to compute, but it's tight enough that it saves you substantial work. You will see this, by the way, in your projects, where you'll come up with some heuristics that are so slow that they actually slow the thing down. Those usually aren't the ones you want. Okay, you might have guessed by now that we can arrange all of our heuristics into a kind of structure where the good ones are the top, the bad ones are the bottom. Formally, these things form a semi-lattice. So in particular, so exact means you actually are using H star. Exact is the best you can do, and in some sense, in terms of admissible heuristics, 0 is the worst you can do, and all the other heuristics will be somewhere in between. More than that, there's a notion of dominance. So we say that a heuristic A is better than, it dominates a heuristic C if for every state H is larger or equal to, right? So there's an equal to, technically things dominate themselves. But you can see exact dominates all other heuristics, everything dominates 0. And there's actually a kind of a join operation here. That is, if I give you two heuristics A and B, right, so this is showing that A is better than C. And if I give you two heuristics HA and HB, and at every point I take the max of them, it should be easy to convince yourself that if they're both admissible, then their max is admissible as well. And of course, it's going to be strictly better because it's either the same or larger than either of them. Right? So that's one way to combine heuristics, is to take a max. Would taking the average be admissible still? It would be, but you should never do that. So you should never add heuristics, and you should never average heuristics. Heuristics are kind of a max kind of thing. All right. There are what are called trivial heuristics. This is important because you'll see this terminology on exams and problem sets all the time. If you're asked for an admissible heuristic and you say 0, you are technically correct. It is admissible, but it's trivial. So we'll ask for non-trivial ones. The top of the lattice, the exact one, is also admissible. It's also trivial in a different way. So we're interested in the things in between. All right. So A star. What can you do? Well, we know you can path, right? That's kind of pathing, routing problems, whether it looks like Pac-Man or it looks like MapQuest or something like that. There's resource planning problems. If you're a robot and you're trying to move, we'll see examples of this later, where a robot is trying to kind of get its arm through some kind of obstacle field. You can solve those things with A star search. In a lot of video games, A star search is used to path. Even things you wouldn't think, like machine translation systems, things like Google Translate. There's an A star search in there looking between the various translation options. Speech recognition. A star search is everywhere. Let me give you a quick illustration visually of how it makes your life easier. So let's see. Here's a plan. Let's go back to Mastermind Pac-Man. Mastermind Pac-Man wants to eat all the dots, and it wants the total number of actions to eat all the dots to be as small as possible. So here we are. We're going to start him computing now. This is uniform cost, 1,000, 2,000, lots of nodes. The nodes go by pretty quickly because there's no heuristic to compute, but 8,000, after 8,000, almost 9,000, almost over 9,000 nodes, okay? And here we get a total cost, so make sure you remember this number. Total cost was 27, and we did it in 8728 nodes. All right, let's see what A star will do. So it's the same board. this is Mastermind Pac-Man armed with A star, and I will start it now. Nodes expand to 175. That's pretty good. Okay, so you see I told you remember 27? Here's the same path length 27, but now we expanded many fewer. And whatever that heuristic did, which I won't tell you because that's part of your project, whatever that heuristic did, it didn't take very long per per computation, right? Okay, any questions on that? Got one more topic for today. Okay, one more topic. All of this time we've been talking about tree search. Remember, in a tree search, every node in the tree is a plan, which means the same state in the underlying search problem can appear many times. And in particular, this idea that there are lots of different paths to each state can cause you to do exponentially more work, which is bad because your search graph was probably exponentially large to begin with. But take a look at this. Let's say we're trying to get to D or kind of get further down in the alphabet. There are a lot of paths to D. If you look at the search tree and your start state is A, what's it look like? Looks like this, right? There's two different paths coming out to B, and each of those has two paths to C. And so there's an exponential explosion as you unroll the graph into a tree. So maybe we shouldn't unroll the graph into the tree. The reason why we do unroll the graph into the tree is on that tree, first of all, in the worst case, there are plenty of problems which are tree structured to begin with, right, where there aren't multiple ways to achieve a state. We'll see some examples of those later. But one nice thing about tree search is it's very easy to think through things like admissibility, optimality proofs are really simple because everything's just kind of moving downward in the tree. What we'd like to do is we'd like to make sure we don't expand all four of those C's. We don't expand both of those B's. In doing that, we're going to be skipping some duplicate work. Once you start skipping work, bits of your tree will never happen. And then arguments about correctness are much more difficult. All right, so let's say we're doing breadth first search. There's some work here that we shouldn't bother doing. So what would we expand in breadth first search? Well, this should be old news by now. We'll expand S. When we expand S, D, E, and P go on. We'll expand one of them next, so we'll expand D. And then we'll expand E, and then we'll expand P. Okay, what's next? We'll expand B, we'll expand C, and then we'll be tempted to expand E, but we probably shouldn't. Why is it a waste of our time to expand this version of E? Yeah, I heard some superposition of lots of correct answers shelled out. It's because we've already expanded this E, and if we're not worried about costs and we're just worried about what states we can reach, if we're only worrying about reachability, there's nothing we can get to from this lower E that we're not already going to find from the upper E. So we don't need to consider both ways. And if this were just breadth first search, we would have a really simple way of speeding up our life. This would in fact be called breadth first graph search, where we simply never expand a state twice. So when you pick up a node, which is a whole plan, you look at its state and you say, have I expanded this state before? And if you have, you just don't. You drop it on the floor, safe in the knowledge that whatever utility you could have gotten from this plan, you're going to get from some other plan that you've already expanded. Okay. So the idea is simple. In code, it's like one line. The idea is you never expand a state twice. How do you implement this? You start off with tree search, but you augment it with a memory, right? You remember all of the states you expand. And remember, expanded means you called the successor function, got the children, and put them on the fringe. All right, so you start with tree search. You augment it with what is called a closed, some people call this an expanded set. Some people call it a closed set. And it is the set of states that have already been expanded. In your book and in many other places, it is called a closed list. It is not a list. Do not implement the closed list as a list. Your search will be so slow, and it'll also be probably timing out the autograder. But if your search is slow, you probably have a closed list. Please don't do that. It will still be correct. It'll just be really slow. All right, so you have tree search. You remember everything you expand. You do what you always did, which is you expand things node by node, pulling things off the fringe. But before you expand a node, you check to make sure its state is new. And if it's not new, you drop it on the floor. That's it. Okay, the third edition book. This is the only time in this course that I know of where the third edition book actually deviates from the lecture and where I think the second edition is a cleaner coverage. If you look in the third edition, there is an algorithm which is correct, but it's a little more complicated and it's very slightly more efficient. you can do whatever you want. The autograder will be happy either way. I actually recommend you stick to the lecture version, which is it's just like tree search, except when you expand something, you check for a repeated state. And beyond that, you stick to the generic version. OK? All right. So very important. The closed set is a set. If you hear somebody call it a closed list, just kind of laugh a little inside at how slow their search is going to be. Do not implement it as a list. OK. OK, we've made a change to our tree search, right? We just made a change to depth first search, to breadth first search, uniform cost, A*, greedy, everything just changed. Now with all of these, when we do the graph search version, the first time we expand a state is the only time we expand that state. OK, can this wreck the completeness of a search? If there is a solution and the algorithm would have found it to begin with, might it now not find it? A little hard to reason about, but this actually can't wreck completeness. And the reason is, if there is a path, right, that path kind of, if there's only one path, you worry about somehow deleting it. But remember, you only ever skip a node if you've already expanded it somewhere else. And whatever path that node had, it had it through its other version. Okay, so a little bit, maybe not obvious on the surface, but this can't wreck completeness. How about optimality? This can absolutely wreck optimality. It's going to wreck optimality in 3 seconds. 2, 1. OK, let's see it. Let's watch A* search. First, let's do a little sanity check here. Let's look at our graph. Yes, indeed, the tree is going to be a little bit redundant because there's 2 ways to get to C. Let's look at our weights. There's some weights there. This looks like a search problem, trying to get from S to G. OK? What do we need to run A*? We need a heuristic. A heuristic is a number that hovers over each state. There's a heuristic. Let's look at our heuristic. Is it admissible? Well, we actually have to stare at it for a little bit, but h equals 0 sure looks admissible. Here, h equals 1 at C, but the actual cost is 3, so that's cool. Here's really the only one that's worrying. The heuristic says 4, and the actual cost is 4. Is it admissible? Yeah, this is admissible. OK, good. So let's do A* search. But remember, we're going to do A* graph search, which means we're going to do our normal search. We're going to keep track of things we've expanded, and if it's ever time to expand them again, we're just going to drop them on the floor. All right, so we start off with our search tree at the root, and everything on the fringe of the tree is the fringe. So we start off with S, which has priority 0 plus 2. OK, so far so good. We pop it off, and something new happens, right? So we have closed set. Did I mention it's a set and not a list? It's not a list. OK, so here's the closed set. Closed set has S in it now. And what do we enqueue? We enqueue S to B and S to A with their appropriate costs, right? Their costs are 1 plus the heuristic. So is everybody happy with this? A has 1 plus 4 as its cost. B has 1 plus 1. All right? Now, what happens? What gets expanded next? B. All right, let's put B on our closed list, and let's enqueue its child, which is C, which has cost 3. Where did that come from? That's 1 plus 2. And then its heuristic value, which is the heuristic value of C, which is 1. OK, so it has priority 4. What gets expanded next? Someone said A, but someone was wrong. It's C. And we put C on the closed list. OK, and now we see that G. So what's on the fringe now? A and G with priority 5 and 6 respectively. And here's where we are. OK, at this point, we didn't declare victory because G, which actually, is this the shorter or the suboptimal path? Is this optimal to G? This is suboptimal. Make sure you convince yourself. It uses the low path, so it's suboptimal. Now, for tree search, this was fine, right? Because it's sitting on our fringe. It's glaring at us malevolently. But A has higher priority, and we're going to explore the entire correct path, and that suboptimal goal is just going to sit rotting on the fringe. OK, so let's see whether this still works. So we expand A. We've never expanded it before. OK, so we pick it up, and we put its child onto the fringe. Its child is a path to C with priority 3. So what comes off the fringe next? C. We pick it up, and we do what? We throw it out because I already expanded it. And what's left on the fringe? Just G. We return it, and we fail. OK, so had this been tree search, it would have been fine because C would have been on the fringe, G would have been on the fringe, okay, these two, and then we would have expanded the optimal goal. Everything would have been fine. Okay, but it didn't work here. Admissibility is not enough when there is graph search. And that's because it's not a problem with the goal, it's a problem with C, right? We locked C into the closed list set. We locked C into the closed set with a suboptimal value. And in essence, the goal inherited the suboptimal path to C. Okay, so we need something stronger. We somehow need things to be right not just at the goal, we need them to be right at every single point. So instead of admissibility, which says the entire path to the goal has to be underestimated, we need a stronger notion that says every little teeny piece, every arc, everywhere needs to be admissible. Okay, that stronger notion is called consistency. So what does it mean for a heuristic to be consistent? Okay, this is an important diagram, and if you look kind of carefully, I'm just going to transplant the problem region of the graph into its own diagram. Okay, but this is also kind of a generic diagram. What do you see here? The green line is the actual cost from A to C. It's labeled 1 because from A to C, it actually costs 1. That's a real graph cost. That is cold, hard reality. Okay, what are these dotted red lines? They are, in essence, the paths that whenever you have a heuristic value, it's telling you something about this kind of dream path to the goal. It's saying, yeah, to the goal, I think approximately this much. So what you've got is you've got 3 paths here. You've got A to C, which is cold, hard reality. You've got C to G, which the heuristic tells you is going to cost 1, and that is in fact admissible. That is a hallucination. That is a dream, right? It's an admissible dream, but it's still a dream. It's not actual costs. And then you've got A to G, which is another dream. It's a dream about how it's going to cost to get from A to G, and your heuristic is telling you 4, which is also admissible. Okay, so consistency is kind of a triangle inequality. I'm going to show you the way it's normally drawn, and then I'm going to show you the way I think is most appropriate in this context. So what you normally say is you normally say the following. You say, what's the triangle inequality? It says kind of the 2 sides has to be longer than the 1 side. So it says the cost from A to C, okay, green means reality here, the cost from A to C plus the hallucination from C to the goal, the forward cost from the heuristic, has to be greater than the entirely hallucinated path from A to the goal, right? So does everybody see how this here looks like a triangle inequality? Stare at that for a second. Okay, what does that have to do with admissibility? I mean, triangle inequalities are all well and good, but that doesn't look like admissibility. But let's say we rearrange this. Let's say we rearrange it to be cost from A to C, and then we subtract. So we say cost from A to C is greater than or equal to H of A minus H of C. Okay, well, what are these things? Well, what's this, right? This is the actual cost of the actual arc between A and C. But what's this? What is the H of A minus H of C? Well, H of A is what the heuristic thinks it's going to cost to finish from A. H of C is what the heuristic thinks it's going to finish from C. And so you can think of this difference as H's opinion of what the A to C part of the journey cost. So you can think of this as an induced cost. This is the heuristic's opinion about the cost of this actual arc. And in the same way that we would like the entire path to be admissible, we also like each of these little induced costs to be less than or equal to the actual cost. So the heuristic doesn't just have to be optimistic kind of in the large scale, it has to be optimistic against every single actual action. Okay, so that's this. I like to think about this as the change in the heuristic. So admissibility is the heuristic is less than the true cost. Consistency is the change in the heuristic has to be less than or equal to the true cost on a single arc. It's like a point-wise admissibility. Okay, so what are the consequences? Consequences are that whenever you travel along a path, right, any path, whether it's going to the goal or not, the F value increases, right? Because you've got some particular node N, or let's call it, it's a parent, let's call it P. You've got some particular node P, and what's its F cost? Well, its F cost is the cumulative cost G of P plus the heuristic H of P. And then you move to its child N. Well, what do you get? You get N being G of N plus h of n, but we know we have consistency, and if we have consistency, that means that this thing has to be greater than or equal to g of n, g of p, plus the real cost from p to n, plus the heuristic back at p, right? So we know because of consistency that as you go along a path, what are you doing? You're basically trading future hallucinated cheap costs in the heuristic for real costs that always cost more than what the heuristic thought. So as you can go anywhere, things get more expensive. It might be even worse than that, because the heuristic could also be screaming that you're going the wrong direction. But it can't get cheaper as you do things in reality, because reality is just crappy, okay? All right, so the result of this will be that A star search is going to be optimal. I'm going to sketch a proof. It's not quite as simple as the previous proof, but the important thing is that you know where they differ. All right, so here's the sketch. There's a new problem. Remember, everything was nice in the tree search world. There's a new problem because it could be that that old argument that says, no, G can't ever beat out G star because everything along the kind of backbone to G star has higher priority than G. Well, the problem could be one of them is missing. One of those things that's supposed to beat G out is gone because it got killed by the closed set at some point. Okay? So we need to worry about that case. So what's the argument look like? There are a couple ways you can do this by induction. There's an alternate proof in the book, but the short version is, well, if n never got born properly, then that's because some n prime, it has a doppelganger out there that gets to the same state that caused that state to be entered into the closed list set, and that state in n prime happened first. So you need to make sure that these kinds of things can't happen. So you pick the highest n in the tree along the path to G star, that this kind of doppelganger beating it happened. You look at its ancestor, the ancestor of n, that was on the queue when n prime was popped, right? There has to be that ancestor, otherwise n isn't the highest thing in the tree with this property. We know, because of what we talked about in the previous slide, we know that the priority of p is that f of p is smaller than f of n, right? And we know that f of n should, if it existed, would have higher priority, meaning smaller f cost, than n prime, right? P being higher priority than n is because of consistency. N being higher priority than n prime is just because it has a lower g cost. That's what optimal and suboptimal mean. And when you chain that together, it means that that point when n prime would have been expanded over p can't happen. P, in fact, would be expanded next. That means n would be enqueued, and now n would beat out n prime. So you have a contradiction. Okay. So basically, it's the old property, but it needs to kind of guarantee that not only the goal is treated optimally, but everything everywhere is treated optimally, and that's why you get this stronger notion of consistency. Okay. To summarize, so I'm going to summarize these properties, and then I'm going to show you a demo. Yeah, question? That's a great question. Let me repeat it for everybody. Maybe we shouldn't be worrying so much about our heuristics. Maybe if we should enrich our graph search so that when we pick up that node and we say, oh, wait, we've done you before, we actually check to see when we put it on the closed set, we check to see with what priority. And if we look and we see this one's actually better, well, we can put this one, right, we kind of put it back on the closed set, but we still in queue. Okay, so essentially you've resurrected this. You've lost your guarantee that each state will only be expanded once, but what you've gained is the ability to recover from an ordering mistake. So the problem with this is this can and very often does cause you not only to re-expand things once, but kind of exponentially often. So in principle, it's a great alternate solution, and it's worth remembering, but in practice, it often causes thrashing, where you re-expand things and re-expand things and re-expand things, and you degrade to a kind of a tree search. But it's a great idea. Yep. All right, so There are more complex variants that you could imagine, and some of them work better than others. The question here was, why don't you try a kind of retroactive surgery? And what becomes complicated is when these things start interacting, making sure that kind of all the ordering properties for all the paths are also propagating to things which may actually no longer be in memory because you kind of moved on to some other region of the graph. You probably get things like that to work, but they'd be substantial variants. The easiest way to guarantee that A-star search will do the right thing and do the right thing in a fast way is to go with consistency, but it's worth remembering there are ways to repair, or you can ignore it too. You can also just accept suboptimality. That's also an option. I mean, the autograder won't like it, but as long as you know you're doing it. For example, in some of the later parts of the project where we ask you, forget optimality, just get close, but do it fast, there it's perfectly reasonable to think about variants like this or to think about inadmissible or inconsistent heuristics. But for the parts where we ask for consistency, it better be consistent. Other questions? OK. All right, to finish up, tree search is optimal when a heuristic is admissible and non-negative and zero at the goal and things like that. But tree search requires admissibility. Uniform cost is a special case because zero is admissible. In graph search, we require consistency. Uniform cost search is still a special correct case because zero is also consistent. Consistency turns out to imply admissibility, so it is a strictly stronger criterion. And in general, if you think of something admissible, it will probably be consistent unless it has the words bounding box in it, and then in project one, it probably won't be. Let me end with a demo, and then we'll actually be done with our first search unit. So remember this? There are no obstacles in the search problem. You're getting from green to red, and the light stuff costs a third as much as the dark stuff. I'm going to run some search algorithms, and you can tell me which one it is. Let's see what we get, just for remembering. What's this look like? So uniform cost is expanding in good directions and bad directions, but faster where things are cheap. What's that? Depth first search. How about that? Greedy. Notice it is fast but wrong. Okay. What's that look like? Oh, it's beautiful. Notice A-star hedges its bets a little bit because it's trying to, at the beginning, the heuristics inaccurate enough that you can try all the extremely cheap things, but it's really quite focused. And I'll show you one last thing, just so you can see what this does. With some obstacles, let's see if you can tell these things apart still. Breadth first search. How do you know? Even progress where things are cheap as when they're expensive. All right. Yeah, that's depth first search. Crazy behavior. Greedy. A-star. Well, it's actually not optimal, so we know it's not A-star. That's greedy search. Notice it didn't go straight to the goal. There's no guarantee it's right. It gets to this intersection, and they both look like they're equally making progress. Greedy, it's not that it can't backtrack. It still maintains a fringe, just prioritizes. Greedy is essentially like depth first search, where you're usually lucky about going straight to the solution. OK, how about this? Uniform cost. Last one. I shouldn't have said that. What's that? That's A-star. Notice it actually expanded a bunch of nodes because there's a bunch of cheap stuff that's more or less in the right direction. Okay, but you got the right answer and you didn't go too far in the wrong direction. A better heuristic would have saved you some time. That's it for search. We'll pick up with constraint satisfaction next time.